Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show a very simple CFD problem using ANSYS Fluent. Actually through this analysis, I'm going to show a structured meshing method using water type geometry workflow. Actually this is new thing, it is introduced with ANSYS 2021 version itself. So for that one we'll take simple geometry and show how structured meshing can be done, and at the same time we'll show its analysis methods, right? Okay, so without wasting time, let us start our analysis. It will be started from Fluid Flow Fluent with meshing. We'll be starting this one with ANSYS space claim. We got this model. For better understanding this model, we can see a sectional view of this and check the model. It is a very simple model. Let us see the sectional view of this one. This is actually a wind tunnel having two exits. From fluid mechanics, we know that the mass flow rate will be more at the bottommost position, and at the uppermost position it will be less. So with the view to have a equal flow rate, we have provided one baffle with an angle of 45 degree with the vertical axis. Another thing is, our aim is to see the flow rate through this wind tunnel. By the same time, we'll see the pressure and velocity distribution through this wind tunnel. In the next video, we'll show the orientation of this baffle by which we can have equal mass flow rate at the two exit locations. Through this analysis, we'll show the structured meshing method using watertight geometry workflow, and in the next analysis, we'll show the optimization method. By changing the orientation of this baffle, we can have equal mass flow rate at the two different exit locations, right? Okay, so without wasting time, let us start our work. So we have already provided some namings to these different sections. This section is known as actually exit 1 and this is exit 2. Similarly, this one is known as entry location, and also we have provided this location. This is one baffle we have provided, right? Next to that, meshing to be done. We want to show structured meshing using watertight geometry workflow. Let us initiate meshing. So it will be better to start with double precision, and as I am using 4-core CPU, so we can consider this as 4 numbers. Let us initiate meshing with structured watertight geometry workflow. This is the interface. This is a completely new interface which is introduced with ANSYS 2021 version. Okay. Initially, we have to import the geometry. This is the geometry. Next to that, we have to go for local sizing. That means if we want any kind of specific meshing size at any specific location, at the baffle size we can provide local meshing, but for simplicity we are avoiding this at this location. If we want to have more numbers of nodes on any specific location, then we should go for local meshing. In this analysis, we are avoiding this local meshing. Let us update that we don't want local meshing. Next to that, we have to generate surface mesh, right? Okay, we can have a better control over the nodes, like we can have maximum size and minimum size, right? Okay, with default conditions, we'll move on to the next stage. That means we have to generate surface mesh from here. Surface mesh is being generated. It is done. Now it is asking some doubts. That means we're having only one solid geometry here. We didn't provide any kind of fluid region. So it is showing that the geometry contains only one solid region. Second one, we do cap openings and extract fluid regions. Yes, definitely. And the next one, change all fluid boundary types from wall to internals. No. And the thing is, shared topology is needed or not. We can go for shared topology. This is a very important thing. That means at the interface, when two surfaces are meeting at that location, we want to have smooth transition of meshes. That's why topology should be shared, right? We want to go for shared topology. It is done. Next to that, we have to go for enclose fluid regions. That means we are having 3 different openings. That opening should be closed. This is actually surface mesh. We want to have fluid volume. That's why 3 different locations which are open that to be closed. because for CFD analysis we want to generate a closed volume, and that opening should be closed with this capping. We are having three different openings. We have provided only names. There is entry, exit 1 and exit 2. Initially we'll select entry, and at the entry location we have to provide actually specific mask flow rate. You can select inlet mask flow rate from this entry location, and you can create cap for this inlet location. The entry location is already meshed. Now we have to provide mesh at the two exit locations, that is exit 1 and exit 2. Let us select exit 1, and exit 1 it will be having conditions for atmospheric pressure at the exit location, so it will be pressure outlet. Let us create cap. It is done. You can see this surface is also closed. Actually we are producing closed geometry or closed volume. Let us select exit 2, and also its condition it is pressure outlet 2. So let us create cap. It is done. Now we got a closed geometry, right? Fine. Next to that we have to create regions, and we know that we are having only single region, so we can update create regions, and it is asking for adding boundary layers. With a default setting we can go for adding boundary layers. If you like we can change the numbers of layers, but with this condition we are going for default boundary layers. It is done. The final stage, that is we have to generate volume mesh, right? So this is the last step. We have to go for generating volume mesh, and in this case we will go for polyhexacore mesh. In case of polyhexacore mesh, as the surfaces are more, therefore definitely computation time will be less. So we are going for polyhexacore mesh, and let us generate volume mesh. Volume mesh is being generated. Actually you can find a very fine volume mesh. It is done. You can see. So orthogonality you can check, it is very nice, right? So we've got a structured meshing method using watertight geometry workflow, right? So our meshing is okay. With this one our analysis setup is ready. Next to that, let us initiate our processing. You can see our model, it is ready. Now we have to go for different processing setup, right? From models you can see it will be viscous laminar flow, as it is not heat transfer problem, so energy should be off, and we are considering this one as a viscous and laminar flow. Next one we have to see for materials. So we can see here default fluid is air and default solid is aluminium. So it's already defined, we are not considering this other material. And let us see the boundary conditions. We can see here like inlet mass flow rate. You can edit inlet mass flow rate. It will be 0.5 kg per second. Let's apply and close. And pressure at exit locations, it will be 0 gauge pressure. To avoid backflow we are considering 0 gauge pressure at the exit locations. Let us edit pressure at the exit 1. It will be 0 gauge pressure. Apply, close. And at exit number 2, again it will be 0 gauge pressure to avoid back pressure. Let's apply and close. Next to that, I'll select methods, and definitely it will be a simple method. We are considering green gauss node based method, and it will be second order. All others will be remain default. From monitors we'll select residuals. To have better accuracy, we'll consider these values as in the range of 10 to the -6. Okay, done. Next to that, we have to initiate calculations. That will be started with initialization, and we're going for standard initialization, and completion will be started from all zones. We can initiate from inlet location also. Let us initialize. Initialization is complete. Next, we can run it. So run calculations, and we want to have 200 numbers of iterations. Let us calculate. Iterations have already started. It will take some time for getting all these calculations. Whenever it is finished, we'll go for post-processing. We'll analyze our results. Okay. 78 numbers of iterations are done. Calculation is complete. Let's go to the next step for getting the results, right? Let us see our results from here. Initially, we want to see contour plot, and we want to see velocity and pressure distribution through this wind tunnel. It is contour number 1. Let us initiate this one from all domains, and we want to see pressure distribution. Let us apply. You can see pressure at different regions, it is different. Let us have it from front end, and you can see that pressure at the entry location is very high. It is in the range of 2.2 to 2.6 into 10 to the 2 Pascal, and at the exit location it is very less, right? Okay. Instead of pressure, we can see velocity also. Velocity is almost constant, it is not varying that much. Pressure is varying actually. Next to that, we want to see the same pattern, pressure distribution, in the form of vectors. For viewing these things, we have to hide this contour plot, and with this default legend view on, we want to see our vector plot. It is vector number 1, and to the whole body it will be initiated, and we want to see velocity distribution. Let us apply. This is velocity distribution, you can see. So with the baffle, actually huge amount of flow is diverted in the top direction. Otherwise, according to principles of fluid mechanics, maximum flow should occur in the first exit location. With the introduction of baffle, we have diverted the flow. In our next analysis, we'll be trying to optimize the flow rate in such a way that flow rate at the 2 different exits will be equal. For that, we have to change the orientation of this baffle. Okay. Next to that, we want to see dynamics of flow particles through this wind tunnel. So for having these things, we have to make this vector plot to be off. It will be streamline and is named as streamline 1. Through all domains, and it will be initiated from entry location. And instead of 25 numbers, we want to make this one more. Let us make this one 50 numbers, and let us initiate this one. You can see this is actually velocity distribution through this wind tunnel. So we can see from the color range that at the inlet location velocity is very less. You can see the velocity distribution through the exit of this wind tunnel. It is very high. Okay. Let us see this flow in the form of animation. It is showing how the flow particles are diverting at the location of this baffle, and after diversion it is gaining high speed. Okay. Let us close this one, and next to that we want to see something else. We want to see volume rendering. And we want to see pressure distribution. Let us view the different settings. It will be with textured application. Let us apply. See, this is actually volume rendering in the form of metallic texture. You can have this one with lighted view. Next to that, we're going to see velocity and pressure distribution at a specific distance away from XY plane, right? So we'll hide this one. This volume rendering should be made hidden. And next to that, we're going to see velocity and pressure distribution at a specific distance away from XY plane. So you can see selection of location. It is a plane number 1, and from XY plane we want to see that distance to be 0.001 millimeter away. Let us create a plane, and the plane is created. On that specific plane we want to see distribution of pressure and velocity. Okay, we'll see this velocity and pressure distribution in the form of contours. So contour plot number 2, and it will be initiated through all these surfaces, and initially we'll see pressure distribution. So this is the pressure distribution at a distance of 0.001 meter from XY plane, right? With this one we'll conclude our analysis. In our next analysis we'll be showing the optimization of this one. That means by changing the orientation of this vehicle, we can see equal mass spread at 2 different exit locations. Okay, thank you so much for watching this video. If you want to learn CFD in a better way, you can see my Udemy videos. Link of this one is already provided in the description box. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.